Welcome to the fifth lecture in quantum field theory. Now, in this lecture, we will discuss the spin and the probability current of the Dirac particle, and we will also talk about the Dirac Hole Theory, which is a consequence of this entire theory, and it will be very, very interesting. It's probably the most interesting thing that we have discussed so far. So do stay until the end, because we do need to understand the other concepts first. So we would like to know what the spin of the Dirac particle is, right? What is the spin of the particle that is described by the Dirac equation? Of course, we spoiled it a little bit in the previous video, but now we're going to do this a bit more formally and see what's going on. So what we know, and some of it we will go through in more detail once we take some time to talk about the Lorentz transformations and just Lorentz invariance in general, but Lorentz transformations, they include rotations, right? And we know, for now, I've mostly been saying it, we will prove it soon enough, as I mentioned, but we know that the Dirac equation is covariant, right? It is invariant under a Lorentz transformation. So what that means is that the rotations, which are part of the Lorentz transformations, should commute with the Hamiltonian of the Dirac equation, so just the Dirac Hamiltonian. And what that means, right, just going further, is that the generators of rotation should commute with the Dirac Hamiltonian. And what are the generators of rotations? I hope that you remember this from quantum mechanics. Those are the angular momentum operators. So what we expect, just because of the fact that the Dirac equation is Lorentz invariant, or it is covariant, we expect that the angular momentum operators, Li, of course, because there are three possibilities, right? Lx, Ly, Lz, we expect them to commute with the Dirac Hamiltonian. Now, what was the Dirac Hamiltonian? Keep in mind, the Dirac Hamiltonian was simply alpha dot p plus beta m. Okay, we defined all these matrices in the past. We will go through them again throughout the video. So this is alpha I, pi. Just the dot product between these components. Now, the angular momentum operators, as we have seen in quantum mechanics, are the Levi-Civita. This epsilon is going to be the Levi-Civita symbol here, ijk, xj, pk, right? This is just a compact way of writing Lx, Ly, and Lz all together. Now, you may already be familiar with the Levi-Civita symbol here. In case you are not, let me show you how you can work with this. This symbol is going to be 1 if the I, j, and the k are even permutations of 1, 2, 3. So what that means is that if we have 1, 2, 3, this is equal to 1. But now if we move two indices, or an index twice, it's still going to be 1. So you can do it 2 times, 4 times, 6 times, whatever, but always even. So for example, if we now move the 1 to the right, basically change the position of the 1 and the 2, and then we change the position of the 2 and the 3, we would get 3, right? We would basically have 3, 1, 2, 3, 1, 2. Right, so what we did here is basically we change the position of these two first, so that the 3 goes to the beginning and the 1 to the end. And then we change the position of the 1 and the 2, so that the 1 goes to the second position and the 2 to the end. And then we can do it once again. So for example, now we can move the 1 to the right, so that we get 3, 1, 2. And then we move the 2 and the 3 to different positions, for example, so that we get 2, 3, 1, right? So there, once again, we did 2 permutations, and in all those cases, we get a value of 1 for the Levi-Civita index here, symbol here. Then we have -1 in the case where we only did one change. So for example, if we simply did 1, 3, 2, right? So I just changed these two. Or if maybe we change the 1 and the 3 and nothing else. So we get 3, 2, 1. And what other combination? If we only change, let's see, the 2 and the 1. So if we get 2, 1, 3. In all these cases, we get -1. And if any of these indices are repeated, we get 0, right? So if I is equal to j, if j is equal to k, or if I is equal to k. If any of them are repeated, we get 0. Okay, so that's what that symbol means. And this is, yeah, it's basically telling us when we get the symbols. If you plug them in for I equal 1 and then you just put 2 and 3 in the other places, it's just going to tell you what the symbols, what the signs, positive or negative, should be, and you get exactly what we were used to. Okay, so this is just a compact way of writing down Lx, Ly, and z in a single equation, and we will use this notation very often in the future because we are using compact notation, right? We have vectors just all put together, and yeah, we're going to want to use that very often. Okay, so now we want to plug this in here, right? So we want to put this into our commutator and see whether or not it commutes. It should commute, and if not, it should give us some sort of condition that needs to be satisfied for it to commute, right? We expect this commutator to be 0. We expect this to be 0, right? Is it going to be 0? That's the question. So let us now calculate the commutator and see what's going on. So first, the part for the generator of angular momentum, that's going to be epsilon, of course, the Levi-Civita, ijk, xj, comma, and now the Hamiltonian. But be careful, because in the Hamiltonian we have alpha I pi, but we are already using the I elsewhere to denote something else. So for that reason, we are just going to, instead of saying I, use the next letter. So we have I, J, K, so the next one would be L. Of course, it doesn't matter which one you use, but, you know, I don't know, just trying to put some order here. Plus beta M. Okay, so now we just multiply through, right? We use the definition here of what a commutator is. So we get epsilon I, J, K, X, J, P, K times alpha L, PL plus beta M minus, then we have the other way around, so alpha L, PL plus beta M, and then epsilon I, J, K, XJ, PK. So first of all, notice that beta is a constant matrix and M is a constant scalar. So what that means is that they are completely unaffected by space derivatives or just multiplying by some coordinate, or, you know, this is simply a 1 minus 1 or 0, so they are unaffected by any of that. So we can simply put them to the front and we would get exactly the same that we have here. So this term and this term cancel out, right, once we multiply through. We can rearrange the order and they will cancel out. Okay, the next part then, we get epsilon I, J, K, which we can factor out, right? We can factor it from both of them. We can commute it all the way to the front because it is a number. It is 1 minus 1 or 0, so we can just put it to the front. And then we have XJ, PK, alpha L, PL, and then minus alpha L, PL, and then XJ, PK. And now notice that this alpha L, we can commute it all the way to the front because it is a constant matrix, right? We defined it for the Dirac Hamiltonian. It is constant. It does not depend on x, y, or z, so we can commute it with the derivative. And, you know, multiplying by x, y, or z doesn't change anything. You can put it to the left or to the right. It makes no difference. And now we can simply take it out. So epsilon I, J, K, alpha L times xj, pk, and PL minus PL xj, pk. Okay, so now how can we further simplify this? Well, notice that this kind of looks like a commutator, right? We have the product of a few things and then the product of the same things but with different order. And we have the pk here that is all the way to the right. So perhaps we could factor it out if we could put pk right there, right? Also to the right. Thankfully, we can commute the momenta because one momentum is the derivative in one direction in space, and the other one is direction in another derivative in another direction of space. And it doesn't matter if you first take the derivative in x or in y or in z, right? The order does not matter. So for that reason, you can simply change the order of derivatives right there. So you can say, okay, this is going to be PL and this is going to be PK, and thus we can simply factor out the PK right there. And what we are left with is a commutator, right? So epsilon I j k alpha L. And then we have this thing is simply the commutator of xj comma PL, right? It is definition, right? xj PL minus PL xj. That's the definition of a commutator. Okay, now what is that commutator between position and momentum? That is something that we know from our good old days in quantum mechanics. That would be IH bar times the Dirac delta JL, right? Because if J and L are not the same, then they commute, right? The space derivative in the y direction doesn't affect the x coordinates, right? Okay, so H bar is of course 1 in our natural units, and then we have pk. So this means J and L have to be the same, so everywhere where we have an L, we have to change it for a J, or the other way around. But I'm going to change L's for J, so this will be alpha J. And now I get rid of it because I've already applied it. And I will just write the pk a little bit closer. Okay, so this is the result. This is the commutator between angular momentum and Hamiltonian, and yay, we did it! Except that it's not 0. It's not 0. We hoped that it would be 0, but it is very much not 0. So what is going on here? What's going on? Well, it turns out that what we need to do is, the angular momentum didn't commute. Well, then there's a very good chance that there is something else. So we have considered just regular angular momentum. We know that there exists a second kind of angular momentum, right? There is a spin angular momentum. And we didn't really consider that here. So we now want to write down how we can represent spin. But we used to represent spin using the Pauli matrices, right? Those were the operators that we used. But now we are no longer in a usual 3 dimensions. Now we are in this weird 4-dimensional space. So we need to find a generalization for our Pauli matrices. Okay, so what we need to do is now come up with a generalization for the Pauli matrices, which were of course the generators of spin. So we will call them alpha tilde, and we will call these matrices sigma I, 0, 0, sigma I. Okay, and we can see that these generalized Pauli matrices are related to the regular alphas. That's why we put this tilde there by alpha I tilde. This is rho, which, in case you don't recall, that's another matrix that we had defined previously. This is 0, unity matrix, 0, times alpha I. Okay, so that's how they relate to the previous alphas that we saw, for example, the Hamiltonian for the Dirac equation. Now, with this at hand, we would like to see, well, does this commute with the Hamiltonian, right? This is supposed to be the generator for spin. So does this commute with the Hamiltonian operator? So let's see, alpha I tilde with the Hamiltonian. So this would be our alpha I tildes, comma, and now alpha. Now we can't use I again, so let's say, I don't know, J. So alpha J Pj plus beta M. Okay, so this is what we now want to see. So multiplying through, you could use properties of the commutators here to make things easier, and we will get to the same result that we'll get to now. But I like to do it in the way that, if you don't remember the properties, you can solve it anyways, but of course I will tell you the property once we get to the result so that you can see how you could have done this faster. So multiplying through, we get alpha tilde I alpha j pj plus alpha I tilde beta m minus, and now the other way around, so we get alpha j pj alpha I tilde minus beta m alpha I tilde. Okay, so with this at hand now, we have, let's see, alpha I tilde alpha j pj, but then we have alpha j, and the pj is in between, right? It's in the middle of our alphas. So if we want to be able to rewrite this, maybe in the form of a commutator, we can commute the pj's, right? So we can commute pj and the alpha i's because of the fact that none of the alphas depend on space, right? It's simply Pauli matrices, they don't depend on space. So the derivatives do not affect them. So with this, we now see that we have the commutator between alpha I tilde and alpha j, pj, so this and that. And then we have, let's see, alpha I tilde, beta m, and then minus beta m alpha I. But m is simply a constant scalar. We can just move it to the front if we want. So we can write this as minus m beta, and we can even write the m on the other side, I guess, just to make this very, very clear. So we can write this as plus, and then the commutator between alpha I tilde and beta times m. So now we need to figure out what these commutators are. Of course, this is the step that you could have done. You could have known that you can, when you have the commutator between two different things, you can separate them, and you can also factor out those constants pj and m. So you could have just skipped this intermediate step, but in case you didn't know, well, there you are. So now let's calculate. So alpha I tilde alpha j. What is this commutator? Well, keep in mind what the definitions are for these matrices. So we just defined the alpha I tildes as sigma I 0, 0, sigma I. And we defined previously, right, the AJs, in this case, the alpha j's, as 0, sigma j, and sigma j 0, right? That is the previous definition that we used when we first defined those matrices. So the commutator between those two would be alpha I tilde alpha j minus alpha j alpha I tilde, and I guess this bracket wasn't necessary. So now we can just multiply these things. So we get sigma I 0, 0, sigma I, and then 0, sigma j 0, minus, and now the other way around, so sigma j, sorry, this is 0. So 0, sigma j 0, and then sigma I 0, 0, sigma I. Okay, so now we just multiply through. So what we get here is sigma I times 0, so we get 0 here, and then 0 times this, so of course still 0. Sigma I, sigma j, so here we get sigma I, sigma j. Then here we have 0 times 0, sigma I, sigma j. So we get sigma I, sigma j, and 0 here, minus, then we get 0 times sigma I, sigma j times 0, so 0 there as well, and then 0 times 0, and then we get sigma j, sigma I, and same thing here, sigma j, sigma I, 0. So what we get is, let's see, so this is 0, and then we have the commutator between sigma I and sigma j. Then we have the commutator between sigma I and sigma j, and we have 0 there. Okay, so what is now the commutator between sigma I and sigma j? That's the commutator between Pauli matrices, which we have seen in the past. Now, of course, we have to write this in a more generalized form, so we'll use the Levi-Civita symbol as before. So this is 2i epsilon I j k sigma k, and 0, sorry, not 0, but rather 2i epsilon I j k sigma k, and 0. So of course we can factor out the 2i epsilon I j k blah blah blah. So this is 2i epsilon I j k times 0 sigma k 0, but this is precisely the definition, right, of alpha k, right? That's alpha j, but if you change j and k, we get exactly the same. So this thing is 2i epsilon I j k times alpha k. So that is the first commutator down. Now we want to go for the next one, which is this alpha I tilde and beta. So now we want the commutator between alpha I tilde and beta. Okay, so here this will be, let's see. So now alpha I tilde, well, we already know what it is. It is sigma I 0, 0, sigma I. And what are the beta matrices? Well, the beta matrices we had defined as, I mean, I guess you could use other representations, but in this representation, it is unity matrix 0, 0 minus unity matrix. Okay? So by doing this, well, and of course, now we need to subtract the other way around. So 1, 0, 0 minus 1. And then we have sigma I, 0, 0, sigma I. So multiplying through, we get sigma I times 1. So we get sigma I. Then we have, well, times 0, 0 times 0. Sigma times 0, 0 times 1. So we get 0 here, 0 here, minus sigma I. Then we get minus, and then we have the identity matrix times the sigma I. So sigma I, 0, 0, minus sigma I. So you can see that from the minus signs, everything cancels out, and we get 0, right? Sigma I minus sigma I, minus sigma I plus sigma I, so we get 0. Okay, so from this, we can go back in here. This part will be 0, that is easy. So this result is just going to be 2i epsilon I j k. Be careful not to confuse these two i's. One of them is an index, the other one is, you know, the regular I that we use for complex numbers. Then we have alpha k and pj. Now comparing this to what we have up here, so now what we can do though, because we want them to look the same, we can change the k's and j's, and we can change the k that used to be there will now be a j, the j that used to be here will be a k. But doing this, because of the fact that we have this index here, right, if we change j and k once, it's going to cost us a minus sign, right? And then we can just relabel, just change the labels again, it doesn't matter, so that we end up with the same notation as above, okay? So basically changing those labels cost us a minus sign because of the Levi-Civita there. And now that we have the same notation, notice what we have, right? So if we want to take the commutator, right? So if we want, let me change colors maybe. If we want the commutator of L1, right, just looking at the results that we have, here we get twice what we have up there and with a minus sign. So let's go for the commutator of Li, right, the angular momentum, plus half, right, so 1/2 of these alpha i's. Okay, and we want to see the commutator between that and the Hamiltonian. So doing this, now again, you could use properties of the commutators to just split this commutator into two. But if you don't know that, you just multiply through LIH plus 1/2, this is tilde by the way, alpha I tilde times the Hamiltonian minus HLI minus H 1/2, which I will move to the front, alpha I tilde. I guess I didn't have to move it to the front, but anyways. So with this, what we have here is simply the commutator between angular momentum and Hamiltonian plus the commutator between 1/2 generalized Pauli matrix, comma Hamiltonian. And we know that the first one gives us this is I epsilon I j k alpha, I think we said alpha j pk, I think. It's not like super relevant, but yeah, alpha j pk. And then we have minus 1/2 times 2i epsilon I j k alpha j pk. So this is 0. So we see that if we take the total angular momentum ji to be Li plus 1/2 of our generalized Pauli matrices, then it commutes with the Hamiltonian, which is exactly what we want. Okay, so with this, we basically see that we do have a spin in our system. Now the question is, what is the spin? Right, so what are the eigenvalues of this operator, right? What are the eigenvalues of the spin operators, right? If we call this thing right here, our spin operator SI or something, well, what are the eigenvalues? So let's see, for example, S3, right? Because, I don't know, we always like to go for the Z coordinate for some reason. So let's go for 1/2 alpha 3 tilde. So this is 1/2 sigma 3, 0, 0, sigma 3. So what are the eigenvalues of this operator right there? Well, the eigenvalues are going to be the eigenvalues of this matrix. Well, what is that matrix? That matrix, right, plugging in what sigma 3 is, it is 1, -1, 1, -1, and well, 0, 0, 0, 0, 0, 0, 0, 0, a bunch of zeros. And since it's already a diagonal matrix, we can see that it has eigenvalues of plus minus 1/2, right? The matrix itself has plus minus 1, but we are multiplying by 1/2. So we have eigenvalues of plus or minus 1/2 with double degeneracy. Right? And why is that? Well, because we have, as we saw previously, two possible energy, right? We can have positive or negative energies. So if we have, for example, positive energy spin up and negative energy spin up, both of them have spin 1/2. But if we have positive energy spin down and negative energy spin down, both of them have spin minus 1/2. So there we go. We just showed that the Dirac particle has a spin of either plus or minus 1/2, right? So the spin itself is 1/2. It is going to be a fermion. And yeah, that's very interesting. So now we'll continue with the probability current. I will just wipe the board real quick. Okay, so now that we have found the spin of the particle, let us now take into account or study the probability current, right? Or what's going to happen here? Why do we care? Well, as we might recall, when we studied the Klein-Gordon equation, well, one of the problems that we found was that our probability current was inconsistent, right? It just wasn't working. And the whole reason we tried to do this equation to study relativistic quantum mechanics that was only of one derivative in time and space was because we wanted our probability current to not have that problem. So let's make sure that that is indeed the case. So let's write down, right? Let's just go through the general procedure to find the probability current. I will, however, do an approach that will introduce some new notation, right? We could do the exact same thing that we always do, just write down so I d psi dt, and then we just continue with our Hamiltonian, right? Because this is equal to h times psi, but our Hamiltonian would be alpha p plus beta m times psi, and then we can take the conjugate of this, and then we subtract, right? And then we multiply by psi, we multiply by psi conjugate, we subtract, we do a little bit of, oh, this is actually a total derivative, right? As we have done so many times, and we end up with the probability current. We could do that thing and it would be correct. But I want to do an approach that will introduce some new notation that we will have to encounter, and it's actually also a little bit faster. Well, it might not be because I have to introduce a notation, but I think it's a good learning opportunity. So let's go back to our Dirac equation in our beautiful covariant way of writing it, right? In this mystical covariant thing that we haven't really gone into in too much detail, but we will very soon. So this is the Dirac equation. Now we will take the Hermitian conjugate, right, of this equation. So by doing that, how do we take a Hermitian conjugate? Well, keep in mind, we have to switch the orders. When they commuted, it didn't matter, but now things don't always commute, so it does matter. So psi Hermitian, and then minus I, whatever the Hermitian conjugate of the gamma matrices are. And then, well, the mu doesn't really, I mean, it doesn't matter there that we take the Hermitian conjugate, but notice that now we have a little bit of an issue because, well, what is this acting on, right? This is kind of weird. What is this? What's this acting on? So yeah, it just looks weird, right? So what we're going to do here is introduce a new notation because these sort of situations will happen often, and what we did here wasn't all that clear. So let me just multiply through this equation right there. So I gamma mu d mu psi minus m psi is equal to 0. That is what we had before. And let us take the Hermitian conjugate here. So here, the Hermitian conjugate will be minus I. Well, we have to change the order. So now comes this thing together, right? So we have d mu psi Hermitian gamma mu Hermitian minus m, which is of course Hermitian. It's mass, it's a real, and psi conjugate equal to 0. So now comparing these two expressions, we can see that what this operator should be doing is basically multiplying this. But if we want to keep this notation, we can introduce a new notation, which is this arrow right there. Right? So if we write it like this, this means that this derivative operator here is going to be acting on that, right? So it is, it's kind of, we are taking the derivative, but to the thing that's way to the left, right? So that's basically what we are doing. And both of these notations are correct. We're going to use this just to get acquainted with it. So now let's try to figure out what everything is. So gamma mu is our main concern here. Gamma mu Hermitian, right? What is the Hermitian of gamma mu? Well, let's go step by step with each one of the components. So let's keep in mind that in our representation, of course, you can choose any representation that you want. I'm going to use the one that we have defined here, which was that gamma 0 is 1, 0, 0, minus 1. You can, of course, use whatever representation you want, and you will get to the same result. The procedure will be quite similar, with just slight differences. And our gamma i's will be 0, sigma I minus sigma I 0. Okay, so what is gamma 0 conjugate, right? Well, what we have to do is transpose our little situation here, and then we just change any i's to minus i's, but we don't have any i's, and this is already diagonal, so the transpose will be itself, so we just get gamma 0, right? So nothing crazy there. Then we have the gamma i's, right? If we want to see its complex conjugate, well, what is this going to be? Well, here we are just going to transpose it, right? So let's transpose it first. So instead of having 0 sigma I, we are going to get 0 minus sigma I, and then sigma I 0. So this is basically minus gamma I. So now we want to find some way of combining these two results into a single expression for gamma mu. Okay, so we want to see what is gamma mu Hermitian, right? A single expression that contains both of these. So here you have to get creative. Now, we know that gamma 0 squared is equal to 1, right? You can also see it right from there. So, right, 1, of course, being the unitary matrix, by the way, just to make this very clear. Okay, so then, how can we do this? Well, notice that if we multiply this by gamma 0, two of them are always going to be 1, so we end up with the result that we know is correct. And if we multiply here by gamma 0, then we can anti-commute, right? We know that gamma I and gamma 0 anti-commute. We saw that when we introduced the gamma matrices. You should know that. The next video will be concerning gamma matrices and the properties, so we will go into depth there, but still, it's good if you know it. Gamma 0, gamma I, gamma 0, right? The anti-commute. So you have to add the minus sign to make up for it. And now we have gamma 0, gamma 0, gamma 0, gamma 0, gamma I, gamma 0. So basically, this is gamma 0, gamma mu, gamma 0. And now we can make sure if mu is 0, we end up here, which gives us gamma 0. And if this is I, we end up here, which we can use to go back there. And this is 1, so we get the correct result. Okay, so with that proof, we can now go back into our little beautiful equation there and just plug it in. So blah, 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 blah. There we go. So let's just plug it in here. So we have psi conjugate minus I, gamma 0, gamma mu, gamma 0, d mu with this left arrow, minus m. This is equal to 0. So now we are going to multiply from the right by gamma 0, right? So gamma 0 there, so that we can multiply it through. So we get, well, psi Hermitian. I combined psi and gamma for some reason. Gamma 0, gamma mu, then gamma 0 squared, because we can commute the gamma and the derivative operator. There's no problem there. Minus m gamma 0. Gamma 0 squared is, of course, 1. And now we have gamma 0 and gamma 0, which we can just take outside from the left. So we get psi Hermitian gamma 0 minus I gamma mu. And then we have, well, del mu to the left minus m equal to 0. And now we can introduce some new notation. And this is exactly why I wanted to use this or do this method, because now I can introduce the Hermitian adjoint here, which will be psi Hermitian gamma 0. And this will behave very nicely, and it's going to make everything much easier. So minus I gamma mu d mu minus m. So we can see that now using this has the same form as our initial expression, right? So this, I'm missing the arrow, by the way. So the initial expression, right, the Dirac equation for psi, and this, they have basically the same form, except, well, we have the Hermitian equivalence here. So using this notation, we get this very interesting kind of equivalent expression. And now, well, we already used that. Let's do what we always do, right? So I'm just going to write these equations together. So I gamma mu d mu minus m psi is equal to 0, and also the Hermitian adjoint of psi minus I gamma mu d mu acting on the left minus m is equal to 0. So now just let us do what we always do, right? So we go ahead, we multiply from the left by psi bar, and then down here we multiply from the right by psi, right? So perhaps if we are multiplying from the left, let's do it like this, so that we, are very clear. Okay, and then we subtract. So we subtract equation number 2 from equation number 1. So we get, let's see, psi Hermitian adjoint I gamma mu d mu minus m times psi, and then minus, but we also have minus minus, so they all end up becoming plus. And we have psi Hermitian adjoint I gamma mu d mu acting on the left, and then plus m times psi is equal to 0. And, well, now we can see that the masses will simply cancel out, and we can multiply through, factor out an I, so we get psi Hermitian adjoint gamma mu d mu psi plus, then we have Hermitian adjoint gamma mu d mu acting on the left psi, right? So this is not acting on psi, this is acting on psi, the Hermitian adjoint psi bar. Okay, so of course, well, we can drop the I, we don't really need it here, it's not going to be 0, so don't worry. And now let's undo the notation for psi bar acting on the left. So we get psi bar gamma mu d mu psi plus, and then we have d mu psi bar gamma mu psi. Now we are back to just regular old notation. And now here, well, this is where we do the ages-old trick, right? We say, well, we have the derivative of one thing times another thing, then the derivative of the other thing times the previous one. So this looks an awful lot like a total derivative of something like psi bar gamma mu psi, right? And let's see if this is correct. Let's just take the derivative to make sure that we did this correctly. So this is d mu psi bar times gamma mu psi. This is what is being derivated. It's being taken the derivative of. I don't know what happened to my English there. Then we have plus psi bar gamma mu, right? The gamma mu is unaffected by the derivative. D mu psi, which is of course the same thing that we had before. That is there, and that is there. Actually, it's the other way around. So this is that, and this is that. Okay. So what we get is this. this thing right here. So this thing right there is what we get, and this is a continuity equation. If we define our 4 density current vector, right, to be psi bar gamma mu psi, then we get d mu j mu, which is 0, and that's exactly the continuity equation that we wanted, right? That's what we're looking for. So let's take a look at the components like we did with the Klein-Gordon case. So J0, which we sometimes call rho, this is psi bar gamma 0 psi. But what is psi bar? That is simply psi Hermitian gamma 0 times gamma 0 psi. So this gives us psi Hermitian psi. There we go. Perfect. There's no problem there whatsoever. What about JIs, right? So the 1, 2, 3, that's going to be, let's see, psi Hermitian gamma I psi. Well, there's not particularly much we can improve here. We can write this as psi Hermitian gamma 0 gamma I times psi. And let's see, this is simply going to be psi Hermitian. And this is what we defined as the alpha i's, right? Alpha I psi. Okay, so that's the way in which we can define those currents. So this alpha, I think we just defined it as alpha vector, actually. There we go. So that is the way in which we can derive or write down these currents. And as you can see, there is no problem with them. There's no time derivatives, which was the case in the Klein-Gordon equation. So these are perfectly valid. Everything is nice. And yeah, this is really good. So by doing the changes that we did, by coming to the Dirac equation, going to this matrix setup, we came to this very, very, very interesting result. And good result, right? However, there is one more problem. There is one issue that we have not addressed, and that is the negative energy values. Because we can have energy that is positive, and we can have energy that is negative. And that is an issue, right? Because if negative energy states are allowed, then, I mean, you know that physical systems tend to go to lower energy states. So that means that even slight perturbations to a system might make it go like spiraling into negative energy states where you have infinity, right? Because you can go all the way to minus infinity. There's always going to be a state with less energy. So this would, I mean, it makes no sense, right? And in reality, we do not ever find negative energy particles. That just does not happen. So what's going on, right? And this is where Dirac came up with something absolutely bananas. He called it I don't know if he called it, but now we call it the Dirac Hole Theory. He said, well, perhaps what we have here is not negative energy states. Or, I mean, perhaps we do have them, but they are not available. Because keep in mind, this theory is for particles whose spin is 1/2, for fermions. And we know that two fermions cannot share the same state. So perhaps what is going on is that all possible negative energy states are already occupied, right? We have an infinite sea. This is also why it's called sometimes the Dirac Sea. So the Dirac Sea. We have an infinite sea, right, of electrons or fermions, depending what particle you're looking at. Let's say electrons, just for the example, that have, right, this is the energy, this is 0. This thing here, there's an infinite sea of electrons that are already occupying every single possible energy value in every single place in space. And since they're already happy in their state, they do not interact. So yeah, that's crazy. That is absolutely bananas, right? Just thinking that everything around us is filled by infinite amount of electrons that are just invisible, that you cannot really detect. It's crazy, right? And it also has crazy implications. Because let's say that you had a photon. You have a photon traveling, traveling through space. Actually, maybe let's draw it outside. Traveling through space, right? And well, by the way, this graph is not particularly accurate. In principle, you have to allow for a gap, right? You have to allow for a gap of mc squared, right? There we go. So that's the energy. So you have a photon just being happy, la la la, I'm a happy photon, and it interacts. At some point, it has so much energy that it collides with one of the electrons that is somewhere below this line. And it gives it so much energy that it can overcome this energy gap, right? And what you will then have is an electron and a hole. That's why it's called the hole theory. You have an electron up here and a hole down there. So suddenly you have an electron out of nowhere. The photon disappeared, it was absorbed perhaps. And also you have a hole that is the absence of an electron, right? It will have the same mass but different quantum numbers. So basically what and this would have positive charge. It is the absence of negative charge. So what he's saying here is that according to this, if you have enough energy, you could create an electron and also a positive version of the electron, or a positron. And this was actually the first time, at least that's what I believe, this was the first time that the existence of antimatter was produced. And even though the Dirac Hole Theory itself, right, the sea of electrons, was later discredited, it makes no real sense, the prediction of the existence of antimatter is one of the great accomplishments of this version of the Dirac equation. And it was eventually proven, right? Even though a lot of people criticized Dirac, it was eventually proven that he was right about this part at least. So yeah, that's the Dirac Hole Theory. It's very, very, very interesting. So I hope that you enjoyed this lecture. If you did, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you on the next video. Thank you very much for watching.